Hello everyone, my name is Yan Chen. My student ID is MAT3 or MAT2509030. Today I talk about the book The Principle of Mathematical Analysis and the example about the Euclidean space. Let's see. The question is the k bigger and equals to, and the x belongs to Rk, prove the extent that y belongs to Rk such that y not equals 0 but x dot multiple y equals 0. Is this also true if k equals k? So the theory we need the dot product in the Euclidean space. So let's see. So we will know in Euclidean space the x can be displayed the f, y, x, x2, x3, and xk. And if the y also belongs to Rk, y equals to yi, y2, 3. Okay. So the x multiple y can be this. So we want the x, the dot product of y and x equals 0. So then we can think about the y3, y4 until yk all equals 0. Then the x, y equals x, y, x2, y2, and when y1 equals minus x2, and y2 equals xy, then x, y equals x2 plus xy, x2 equals 0. And this equation at least k bigger or equal to 2. And so let me see, when k minus equals 1, what happened? Then x multiple y equals xy, yi, and x equals xy, and the interval all scalar. So when x multiple y equals 0, so xy equals 0 or yi equals 0, or all of them are 0. So, but the question has say the y didn't equals 0, so the only when x equals 0, then x equals 0, then it will be true, but x, the question not requires the x must be 0. So only when x equals 0, it will be true. So we can make the conclusion that when k bigger than or equal to y, then the extends y belongs k, then x multiple y 0. There extends y as k. So 1 equals to 1, then there not be a 0. When k equals 1, only when x equals 0, then it will be true. So when k 1, the proposition is the statement is not true. Okay.
Hello, this is Junker on MAT2509007, and it's my presentation about number analyze, chapter 2, unit 1. Part 1, what is a function? A function is like a rule that connects two sets. If we have a set A and a set B, a function f takes an element from A and gives back an element from B. So we write this as fx. A is called the domain, and all the values fx together are called the range. If every element in A goes to a different element in B, and we call the function 1-to-1. If a 1-to-1 function also covers all of B, we say A and B are equivalent or have the same size. We write this as this A equivalent to B. And part 2 is about finite, countable, and uncountable sets. And we let J be the set of all positive numbers like 1, 2, 3, blah blah blah. We say the set is finite if it has a limited number of elements, like a set involved 1, 2, and 3. And we say the set's countable if it's infinite but can be listed in a sequence like J itself. And we say the set is uncountable if it is too large to be listed even in an infinite sequence. So we make some example, like the set of all integers is countable, and we list them like 0, 1, -1, 2, -2, 3, -3. This show a 1-to-1 match with J. There is an interesting fact. A finite set cannot be the same size as one of these smaller parts, but an infinite set can. These integers are the same size as just the positive integers. So there's a theorem. If a set is countable, every infinite part of it is also countable. And part 3, operation on sets. We can combine sets in two ways. Union, like all elements from any of the sets, and intersection, only the elements common to all sets. Their operations follow rules similar to addition and multiplication, like or A and B or C equals to A and B or A and C. So we have the theorem. If you take countable numbers of countable sets, their union is still countable. And there's part 4, the uncountable sets. Now the exciting part. Consider the set A of all infinite sequence made only of 0s and 1s. For example, 1 0 1 1 0 0 1 blah blah blah. It's all about 1 and 0 and so on. And Cantor proved this set is uncountable. And here is the proof. Now we build a new sequence S. Look at the first digits of S1. If it's 1, make the first digits of S 0. If it's 0, make it 1. So the same for the second digits of S2 and so on. This new sequence S is different from every sequence in the list. So S is in A but not in the list, a contradiction. Therefore, A cannot be listed, so it is uncountable. So we make a conclusion. This means there are different sizes of infinity countable infinity. Like the integers is one kind, but the set of all consequences of zeros and ones is larger. It's uncountable. This was proved by George Cantor in the 19th century using his famous diagonal argument, and it's changed to mathematics forever. And that's my presentation.
Hi, my name is Jiang Zhuoyan. My part is about the matrix space. So I will give the problem about this and solve it. And before we go through the problem, let's look at this theorem. It's important that a set E is open if and only if its complement is closed. And we will use it in our problem. Okay, let's take a look at the problem. And my problem is from the exercises in chapter 2, 2.19. And let's this is a problem. Let S be a matrix space with matrix D. If A and B is disjoint sets in X, prove that they are separated. Okay. The problem A is easy and we know that A and B are closed sets in X, and we know that the closure of sets of A and B equal to A, B, and by the disjointness, the A intersects B is empty, so A intersects B intersects the closure of B is empty, and the closure of A intersects B is empty too, so they are separated. Let's look at problem B, and we need to prove the same for the disjoint open sets. The sets become open, okay? So now we can use the theorem and change the B into the similar way. And we know that the complement of an open set is closed, so X minus A is closed and B belongs to this. And since closed sets contain the closure of their subsets, the closure B is belong to X minus A, and that A intersects B is empty. So Yes, similarly, we use the same way. We also can imply that the closure of A intersects B is empty, so they are separated. Okay, problem C, because P belongs to S, and the the delta the delta Okay, let's look at the problem C. Fix B belong to X. The delta is larger than 0. Define A like this and B like this, and prove that A and B are separated. So we now first solve the difficult condition that A intersects the closure of B is empty, and because the closure of B we can't know it immediately, so we prove this part by contradiction that so we assume that there exists X belongs to A intersects the closure B, then dpx is less than delta. Yes. So this is an limit point of B. Okay. Now we will use the inequality to prove that it's a contradiction, and we let the epsilon equal to delta minus dpx, and the neighborhood and epsilon x y belong to x, the dxy is less than epsilon contains the sum y epsilon b and y, and so dpy larger than delta, and we use triangle inequality, we can find the contradiction. dpy is larger than delta, but we use the inequality. dpy is less than dpx equals dpx plus dpy is less than dpx plus epsilon. Okay, it's equal to delta, so it's contradicted. Next, it's easy to prove the closure of A intersects B is empty. We found the closure of A is Q belongs to X dpq is less than delta, and it's absolutely that they can't intersect. Yes. So these are the proof, and therefore A and B are separated. Look at the problem D. Prove that every connected matrix space with at least 2 points is uncountable. So we let X be a connected matrix space with at least 2 distinct points P1 and P2 belong to S. And we want to prove that X is uncountable. So we best to create an injective map to the uncountable sets. So these are our way. And let delta 0 equal to dp1 p2 larger than 0 for any delta larger than 0, less than delta 0. Define A delta and B delta like this by parse A L delta and B delta are separated, and we know that X is connected, so the union of A delta and B delta is not equal to X. So there exists X delta belongs to X minus the union of A delta and B delta, meaning dp1 X delta equal to delta. So the map is injective, and yes, so we found the injective map, the interval, the open interval 0 to delta 0 is uncountable, so the X must be the uncountable. That's all my solution. Thank you.